Camps on everyone. Switch on camps. Let's start off. Sure. So this was the last thing that we did, and let's go ahead with the question. So we have a wire here. This is a current wire.
Recording in progress.
That is an infinite current wire. I coming out of the plane. So here you have some random wire whose coordinates are, let's call this is point A, x1, y1, and this is point B, which is x2, y2. This is carrying current small I. Find the force on the curved wire. Let's get this. Others, keep your cams on. Think about it. When can you use effective length? Whenever you say projectile length, first ask yourself, when did you use it? When force per unit length was constant. Prove here also force per unit length is constant. We don't need to prove it, Adrit. So, how are you so confident I can use projectile length? Sonic closed loop is 0. I already learned that. So you mean to say B is same everywhere, right? How do you do this thing? What is the force between the wire which is passing, out of the origin and that random weird curve? It's not so clear. The moment I get a random weird curve, it has to do something with the coordinates only. It doesn't matter the shape. But it still doesn't mean you have to use projected length here. It doesn't work. Projected length use करने के लिए the main idea was, if you remember, the reason why we could use was ILB, the B was constant. The B was not changing anywhere. Here, first of all, forget about B changing. If you look at the field due to this guy, the field is this way, the field is this way, and how is the force? The force is also weird. Force is into the plane. That is still okay. But if you can see, B literally changes direction and magnitude everywhere. So this is what we do. I'll do one thing. I'll just take some better curve. So let's say this is A, this is B. So from here, due to this point, the field here is this way. This is your magnetic field B bar. Let this distance be R. Here, take a small length dl. Okay, and then let the angle between these two guys be L cross R bar, no? Theta. Uh, uh, okay, now look at this thing. So you took this is your R. If you take a small angle here, d theta, this length will be your R d theta, that is B ka direction. Let this angle be theta, so that R d theta and B are in the same direction. So this is something like your dl, and this is your saying theta. So you can say R d theta cos theta is dl. Is that making sense? Meaning the vector is like this. So this is your R d theta, which is tangential. DL is something like this, and you're saying this is the angle between them. So that R d theta ka projection on the tangent is this thing, R d theta cos theta. Is that making sense? I should draw a little bigger curve. See. I'll just exaggerate the figure here. This is your magnetic field. DL bar is in the direction of the loop. This is your DL. When you say R d theta, remember R should be same, right? To make it as an arc length, you should take a radius R and rotate it. That means this entire, the black line, that is your R d theta. Is that making sense? You can't say this is R d theta. The radius is changing from here to here. And we took this angle as theta. So R d theta ka adjacent side is the DL. So R d cos theta is DL. Is that clear?
So that triangle which you are referring to, जिसमें आपने cos theta लगाया है, नहीं वो वाला नहीं
Uh-huh.
चाहिए. The triangle with the B bar or the red
Uh-huh.
dotted line and the black dotted line.
Uh-huh.
That's a right angle triangle now, so we cannot say that the radius remains constant.
Arey, you're taking very small R d theta. Right?
So still no, the triangle is not a circle, so we cannot say that. If you want to take R constant over there, it won't be along B exactly. It will be somewhere B के अलग होगा. I think we cannot neglect that.
D theta is very small. That is the
Because
whole
that's
point. That is the whole point of the assumption. Okay, tell me one thing. In a triangle, if this angle is 0, what are these two angles then? And both the sides are equal.
90 and there. ठीक है
क्या
समझ
problem
गया.
is there?
हाँ नहीं ठीक है.
तुझे ना सब जगह डी थीटा कभी प्रॉब्लम नहीं आया, आज प्रॉब्लम आया तुझे डी थीटा 90 डिग्री से, हैं?
See, today it just made less sense, but it's fine.
अल पंची वही बोल रहा हूँ, पहले जब मैंने व्हेन आई ड्रॉट सच अ स्मॉल वन नो वन वाज एबल टू सी, तो आई मेड इट बिग। बोल रहा हूँ ना, आई एम एग्जैगरेटिंग द फिगर, इतना ये नहीं होता है रे नॉर्मली। हाउ इज दैट थिंग व्हिच आई सपोज टू ड्रॉ सपोज टू बी लाइक दिस। अभी मैं ऐसा ड्रॉ करूंगा, क्या दिखेगा? Clear with this thing? Understood? Is that also is very much that is not looking like a triangle? Obviously, it won't look like a triangle and the circle at the same time. So what we are doing was, when d theta is small, you can assume this arc length also to be a straight line.
हाँ सर
It,
समझ गया वो तो
it,
होगा।
it becomes both. So yeah, but did what is this? Okay, so this is clear. R d theta thing. Great. Now, what is the force? So the small force on that arc is current small I dl cross b bar. So I is I only, dl is dl, which is r d theta cos theta. And what is b bar? Mu naught I by 2 pi r, that is a field due to the infinite wire. And what's the cross product here? And the angle between them, that is b bar and d bar, that is sine theta. Mu naught I dl cos r. Dl cross r bar. Yeah, did I miss something here? Theta is coming now. ठीक है, I think that is the thing. So this is I dl, b bar is mu naught I by r, and the angle is between dl bar and b bar, that you to get as theta. So this, and what is the direction? Minus k cap. So luckily all are in the same direction. R will cancel. So that is the first thing that will make your life easy. And I think then you are done actually. हो गया ना? That is integral sine theta cos theta d theta, which you can integrate. This is capital I. I don't know why I'm getting a weird feeling this might be wrong. Hmm, looks fine. So this would be mu small I by 2 pi. That would be sine theta cos theta d theta. This is the force on the wire. This filaments will go from, we will see what are those angles. Theta 1 to theta 2. How much is this? Mu naught I by, you can write that as sine 2 theta, right? How do I take this component? Should I take DL ka component on B or B ka component on DL? I think I'm goofing up something here. When you take any random vector here, you can represent this into two parts. dr bar and rd theta bar. I think I'm writing reverse actually. This thing, right? You have to represent dl bar into two components. So let me show you how that works.
So why is whatever you did wrong?
Nay, whatever I did wrong, nay, I'm just goofing up these two parts actually. We should take who is the which component. Do you remember this polar coordinates which we did?
Yes.
In polar coordinates, normally when we take
तो ये कब किया था?
vectors when you're not there,
Okay.
we hit that in basic maths. So basically polar coordinates in this thing, the vectors are right. इसमें भी किया था रे हमने electric dipole में किया याद नहीं है? ER cap, the radial vector and the tangential vector is RD theta, E theta cap.
हाँ, No
We
idea.
did that thing. We did this thing in electrostatics में. Dipole में I taught you while differentiating that stuff. Here. Remember radial direction, tangential direction. This is a polar coordinates का differentiation.
Okay. हाँ, ठीक है यार.
So basically, whenever you have a vector, right, anything, you can represent this into two pieces. If you have a vector here, something like that, so this can be written into two pieces. That would be dr. So if this was a circle here, this was your rd theta, and this was your dr. Correct? So that is how you can represent a vector in two forms. That is what I was goofing up. I wrote reverse actually. So dl bar would be, we have a component which is dr, that is along the radius er cap, and rd theta, e theta cap, which is a tangential component. We did everything fine. That one bar I goofed up, the whole thing went for a toss. So I should not take, I should take dl ka component on b bar. I'll draw it again. So we have a vector here, which is, this is your dl bar. That thing looks like 90. Let's say this is your dl bar. So from here, when you take your r bar, so this would be your radial direction er cap, and this would be your tangential direction e theta cap. Isn't it? What is radial direction? In the polar coordinates, this is away and this is in a circle, isn't it? Now it's saying something.
हाँ सर बट हमने जो किया था उसमें क्या गलत था?
Which one?
The previous one which we did.
No, previous one is not wrong. अब आएगा. वो mistake कर रहा था मैं. So this was RD theta, right? This was R and that was RD theta and this was DR. ठीक है. So what I'm saying is DL का component is RD theta.
अच्छा हमने उल्टा लिया था.
हाँ, मैंने वो mistake किया था. मैंने RD theta का component DL ले लिया था.
I see.
So you divided DL into two directions, tangential and radial. So you should get DL का component as RD theta.
Okay.
Right? Oh, catch the bus. That was the thing I was goofing up. So, and how is your magnetic field direction?
तो सिर्फ पिछले वाले में we could have written dl equal to rd theta sec theta then हो जाता.
हाँ बस हो जाएगा, वही करना था.
Okay, okay.
So but if I write like that, then Ishan will come and say, "Sir, why did you do like this thing?" So I thought first only I'll show you before. This will be DL bar. I'll take that direction. So it is a DR bar. Na, I hate these directions. This diagram is not coming proper. How do I show this DR bar? This is better, I guess. Okay, I'll just take one direction. I'll just take negative sign. We'll ignore that. Okay, let it be. Let's not worry so much about it. Anyway, it's going to get cancelled. So that is there. And how is the magnetic field? The magnetic field dB bar, that would be in this direction, isn't it? So here the magnetic field due to the wire is given by mu naught I by 2 pi r, and that will be in the tangential direction. Clear with this? Then you're done. What is the force? Force is equal to current I dl bar cross b bar, and this would be dl cross b. So if you're doing a cross product, the dl bar can be written as, so when you do the cross product, only which component will come into the picture? So dl and e theta component will become 0. So only that is left is the er component. So that would be I, and dl would be r d theta e theta cap plus dr er cap cross mu naught I by 2 pi r e theta cap. Parallel vectors will be 0. E theta cross e theta would be 0. So the only thing that is left is I mu naught by 2 pi r dr. This is what I remembered. This is a force on a small wire. वही लग रहा था, साइन क्यों आया? This would be mu naught I by 2 pi dr by r. So now if you integrate the force on that wire, this would be mu naught I by 2 pi ln r. Limits will go from Ra to Rb. That is nothing but root over x2 square plus y2 square by root over x1 square plus y1 square. So what matters is only the distance from the corners. It doesn't matter what direction is in, what is the shape of the wire. Where Ra and Rb are simply these distances. Again, see what we did, I'll explain. If you take a DL bar, right, I can split this into two parts in the radial polar coordinates, the dr bar outside and rd theta, right? And this can be written as dl is one radial component and one tangential component. Magnetic field is always tangential, it is going in circles. So when you do cross product, only these two things will come, the e theta will go off. And that was the main thing of doing in that way. And then you're done. You become independent of the shape. So you know how they'll ask you this question in the exam? Have a look at this, I'll show you an example. So वो भी है था, you know, we don't want to get into the theta part. Once you write er e theta, that will take care of it. So let me show an example. The question would be framed like this.
Sir, how can we decide the direction with polar coordinates?
We normally देख लेना God, you know, the current is flowing. It depends on what is your eye. So you can just take one small wire here. What is the magnetic field here? B is this way, so I cross B is down, right? Magnitude तो आ जाएगा भाई से. So you can find the direction just from right hand rule. Right?
Not
And फिर
coming
भी polar
anywhere.
coordinate. What?
By
If
integrating,
you,
it's not coming in any.
why will integration give you direction, right? Cross product ER R cross E theta will give you direction, right? ER and E theta. What is this thing? Into the plane, right? Why will integration give the direction? The cross product will give you the direction. When you do this thing, ER across E theta, what are you getting? This vector ER cap, and this is E theta cap. So right hand rule, what will you give you? It gives you a into the plane, if that's what you want to say. Happy? Clear, Advait? Clear, na, Advait? Yeah. Then let me see. The idea for this thing, right, is actually I saw a question somewhere. Answer though they gave it pretty easily, but after that I felt like we could have done it better. Suppose if you have an elliptical wire. So this was a question that I saw, and that we derived it for a general wire. So elliptical wire, which is x square by a square plus y square by b square is equal to 1. Be very careful, huh? This is strictly valid only, in a very special case, like the current should be out of plane and the wire should be in the plane. Accidentally, agar apne wire aisa le liya, you won't get an answer. It will be something else completely. So this we derived for these kind of conditions. So it's a part of an ellipse. So the question was, find the force on the elliptical wire. So if you look at the coordinates here, this guy was a comma 0 and this guy was 0 comma b. Now from the formula which we derived, force would be mu naught capital I small I by 2 pi ln that length, right? So a by b, whichever is bigger, and direction you can take it from here. This will be k cap. Because due to this, the field is this way, current is this way, I cross b is out of the plane. Previous page, I'll show you. There. Meaning the answer comes pretty neat for an elliptical wire. I could have taken any wire from here to here, answer would be same. There, have a look at this page. The ellipse was the actual question.
So we should remember it as a result or what, like this?
If you can remember, it is better, because exam, I don't think you'll be able to derive this.
So can you also go to the page before this?
Did we do this one also? Did we do the point where the wire was perpendicular? That we didn't do. So we'll do that now. Clear? So this would be a tougher one. The easier version is this one. We have a current wire here, and this is small I in the same plane. And this. Let this length be D, and let this length be, let's call it A and B. This way, it's a small wire going I to B. So this is an infinite wire. Find the force between them. If they want to ask it simple question, right? They'll ask you in which direction will this move and which direction will it rotate. So find the force on the small wire and torque on it about the axis, and torque on the small wire. Whenever I ask you torque, I have to define the axis also. Torque on small wire about the infinite wire. Means I'm taking the infinite wire as an axis of rotation. Yeah, about an axis. Perpendicular to plane and passing through infinite wire. If it is a couple, it won't matter. Means I'm choosing this is my axis of rotation. Let's get this. Here also get a longer term. Torque कितना आ रहा है? So this is what we do. At a distance x, take a small piece dx, and due to this guy, the magnetic field will be into the plane b bar, which is mu naught I by 2 pi x. And if you look at the force on this, it will be upward. And if you notice, right, the force is constantly decreasing. I hope you notice that. The force is not same everywhere. Because as you go away from the wire, the magnetic field drops, so the force will decrease on this wire. And how much is that? So the small force acting dF will be ILB. So small I, length is dx. Both are perpendicular. So B is directly mu naught I by 2 pi x. Integrate this. So this would be mu naught capital I small I by 2 pi integral dx by x. Limits will go from A to B. Mu naught I by 2 pi ln B by A. So what is mattering is end of the day, the distance there. That is one. And what about the torque? So torque is nothing but x into the distance into df. So you'll get one more x here. Mu naught I by 2 pi dx. I think this is coming nice. So it's a small torque. Now if I don't define the axis, I can't tell what is the torque. Depending on the axis, that this distance will change. So you can clearly see here, this guy is going to rotate this way, isn't it? It is rotating clockwise. It goes up and rotates clockwise. That way. That itself is a question in the exam. Which of the following options is right? They'll say it will go up clockwise, goes down anti-clockwise, goes towards the wire, so something of that sort. Clear with this? This is an easier version of what we did before, like, when the wires are like perpendicular like this. The previous one is a little different. Because for this thing now, what people started doing, people started coming up with this logic actually. They started saying you can take a wire like this and we'll find the force on this, it is zero, meaning it looks fine. Then basically people are using projector length and getting answers. But the point is, the magnetic field is not constant, right? In that formula ILB, the V is getting messed up. Luckily, here getting the answer, you know why? When we took that formula there, that The R is still there. It is changing. We came the answer that way. But projected line doesn't work here.
So previous method से थीटा के लिमिट्स क्या होती?
Which one?
मतलब इसके पहले we are doing dl equal to rd theta sec theta ना?
Hmm.
So project I mean theta के लिमिट्स.
Theta ka limits will be this angle, na? Tan inverse y by x by tan
But
inverse b by.
थीटा कुछ और ही लिया था ना?
So no, we have to take theta here only, na? B dl hoga. This is your dl. This is b. So it depends on how you're choosing your theta now. If you say this is theta, 90 minus theta,
उसके proper limits you won't get ना, कहीं भी कैसे भी change हो रहा है.
वो चूज करना पड़ेगा. That will be pretty messed up. इसीलिए तो वो लिया नहीं मैंने. I just kept it in polar coordinates. This is an easy one. Do remember this thing how to do. B part is easy. Clear? Next one. We have a big loop here, current I. Radius R. So this point mein current is coming out, huh? And here the current is going down. So in case if you see it in another way, actually I can see it both the ways at the same time, so it's confusing. So the current on the top is coming towards you, and the bottom the current is going inside. So you can figure out the direction there. So at a distance here, x, we kept a small loop here. Radius small r, current small I, and r is much greater than r. So this thing has a mu bar like this out of the plane, and this guy is making an angle theta. Find the torque and the force acting on the small coil due to the big coil. Since r is much smaller than small r, you can assume almost the field on the axial line is uniform here. That is the whole point about giving that r is much greater than small r. Because remember that formula, we know the field formula only on the axial line. So if you take an area like this, I don't know what is the field at remaining points. Since r is very small, I can assume the field is almost same and all points on that. Find the torque and the force on the small coil due to the big one. So the big coil is producing the big one is producing the magnetic field. In that magnetic field, you kept a small coil. So that is experiencing torque and force. Find the force and the torque at this instant. X and theta are given. Theta, x, and theta are variables. How do we do this? What is the torque on a coil formula? You know that mu cross B, isn't it? So due to this big one, the magnetic field B will be mu naught I R square. This is mu naught. I'll do one thing. I'll just take this as a vector area bar. Mu naught I 2 into R square plus X square. The magnetic moment of this small coil will be number of turns, that is 1 I into pi into small r square. So what is the torque? Torque is equal to mu cross B, which would be I into pi r square into that magnetic field B, and the angle is sine theta. Straightforward. Torque is the easiest part. How do you get the force? And remember, force in a uniform magnetic field is 0. Here, even though we are assuming it to be constant, the field is still non-uniform. So there is a force on the coil. Torque is straightforward. Mu cross B and you're done. How do you get the force part? And we did this thing in electric dipole.
हाँ
Anyone
sir, I
remember?
send you something sir. अब प्रोसेस देख
What
लो
did
एक
you?
बार, फॉर्मूला याद नहीं है मुझे.
Then why are you sending?
The process is confirmed because he wrote the formula, so I can try again.
I forgot the field of ring at equatorial point. So exam ऐसे करके आओ, फॉर्मूला सब भूल जाओ. You write down the hints for the examiner to solve.
And तो यहाँ पे 3/2 भी होता है. I think
Idea
थाना
तो right
नीचे.
ही था. Think.
Sir,
I'll
in the
ask you one
formula he
thing.
wrote in
See,
red color.
हाँ ठीक है. 3/2 भी आएगा.
हाँ sir, what he was.
That you remembered. So think about it. When you say the torque on a coil, so in that there are only two formulas. Remember, one is what? Torque, and another was potential energy. Do you remember any relation between potential energy and force? You know,
F is equal to minus dou u by.
बस हो गया, वही
U
करना
is
था.
equal to
So
minus dou f by dou x.
potential energy is minus mu bar dot b bar. So in this case, it would be minus I pi r square b, and that angle is cos theta. So force is nothing but minus du by dx. So this would be I into pi r square cos theta. All these are constant. The only thing that is changing is your magnetic field with respect to x. Differentiate dv by dx and substitute, you'll get the answer. It's not a tough question, but that idea click on I can take potential energy and differentiate. And we did something like this in electrostatics. Mein, remember this question? Force on a dipole due to the ring. We did the same thing. We took the potential energy and we differentiated. It was the exact same idea. Charged ring and electric dipole. Here it is a ring which is producing magnetic field and another coil in it. This is what I keep saying. You won't be, you won't learn everything new. You must have seen things before. We are just repeating in a different way. Clear? It was easy. It's easy to solve, but this thing I had to be careful. The mistake here, right? Just be careful with that. Force on a uniform field is 0. Here the field is not uniform.
So how will the force be acting like in this case?
This is a radial force, right? d by dx. So this is the force along the x-axis.
Okay.
If you want in the y direction, उसके लिए क्या करना है? Dou u by dou y, remember? Actual force का formula याद है? F is equal to minus dou u by dou x I cap minus dou u by dou y j cap minus dou u by dou z k cap. That gives you all the three components.
Got it.
But since our coil is only getting changed in the x direction, right? So what you're getting is only the force in the x direction. Okay? If somehow, if you can give me b in terms of y, then it's a different story. We can't find that. So here b bar is not uniform. Even though we are assuming it is uniform for the, because the coil is small, in reality, it still there's a difference. Clear? Next one. We have a infinite current carrying wire. You projected this with a speed u. So we took a particle here plus q, m. This is speed u. Due to this, the magnetic field will be out of the plane and this will go down. So in this, if you project a particle q, m with speed u, this will start going like this and will take a turn and go off. It won't be a circle because v is changing everywhere. This distance is your x minimum. This is the closest you can get to the wire. This was your initial distance d. So this particle was projected towards the infinite wire with speed u, charge q and m. Initial distance was d and that was your x minimum. Find the minimum distance between the wire and the charge. This won't be a proper circle because b is changing every instant. Let's get this. So we are combining here the magnetic force of the particles which we did with the magnetic field due to a wire. Try, I'll give 2-3 minutes. It's an integration. Like there is no logic, kuch nahi, brute force solving it is. There's no easy way to see and say like, oh, this is what will happen. If you have to solve this from the options, I mean, if you put u is if you put u 0, the answer will be d, right? It won't move only. That much you can say. And second thing,
You have to
if
find
you want,
x.
you have to find x minimum in terms of t. So I'm just trying to guess if this comes in the question and there are options. I'm trying to see what I can do. If I put options when u is 0, the x minimum will be d. And if I put u is infinity, then x minimum will tend to 0. Because the closer you get, the magnetic field will tend to infinity. So it will definitely take a turn. So if you want to touch the wire, you need infinite speed. This much I can guess. Now we have to put them in the options and see which one will match. Luckily, 3 eliminate ho gaya, so great. They don't eliminate, so you'll solve. D by QV plus 1. That's such an interesting answer. That's not an answer. Something remains constant. What is that?
Okay.
Don't say charge and mass, I'll punch you. Say something better.
Okay.
Can I try?
You can just
Angular
type your
momentum.
answer. It's
Sorry.
alag level god hai.
Sorry, sorry,
Lakshika,
sorry.
you are right. Speed remains constant. Work done by magnetic force is always 0. Velocity changes,
Even
be
angular
careful.
momentum will remain constant, no? Why
Hai,
not?
MR cross V. There is a force, there is a torque. Okay, chalo, I'll ask you one thing, Ishan. When you say angular momentum is constant, about which axis?
About the wire?
Dekha?
Nahi.
Ho gaya?
Yeah.
The moment, before uttering the word angular momentum, you have to ask yourself, which axis am I talking about? So don't use that word very lightly. It's a monster. You open the cage without taking precaution, it will eat you, and then you're gone. Speed will remain constant. Work done by magnetic force is always 0. How do we approach this thing? So let this be I at a distance x here. The magnetic field will be out of the plane. So B bar is equal to mu naught I by 2 pi x k cap. Right, and then let the velocity V bar be Vx I cap and Vy j cap. The signs will take care of them. Vx, Vy are variables. So in this entire process, since work done by magnetic force is 0, speed remains constant, which will be root over Vx square plus Vy square is equal to U square, which is constant. Speed doesn't change. So the force on this thing would be QV cross B bar. This would be QVx mu naught I by 2 pi x. V cross B, na I cross k cap is minus j cap. Then QVy mu naught I by 2 pi x. J cross k cap is I cap. Here, if you observe this motion here, you're taking at any instant here. At this position, when it is taking a turn, what is there here? At this term, when it is taking a turn, Vx is 0 and Vy is equal to U. Agreed? There is no horizontal component because you can't get closer than that. The horizontal component must have been 0. That's your limiting condition there. And initially, what is the condition? Initially, Vx is U and Vy is 0. So these are your values. So one thing is clear, I want x, right? So let me do everything in terms of x only. So force is equal to max. That would be qvy mu naught I by 2 pi x. That's your this thing. So we get acceleration ax is equal to q mu naught I by 2 pi m vy by x. So the problem, I don't want that vy. So we'll replace that here. Q mu naught I by 2 pi m. Vy will be root over u square minus vx square by x. Right? And what is ax? V dv by dx. So I'll do one thing. This whole term here, let's simply call it z. Now this guy will be ax is v dvx by dx is equal to z root over u square minus vx square by x. Make sense? Now I know everything in terms of x and dx. So bring it down here. Vx dvx by root over u square minus vx square is equal to, that is z dx by x. Limits. When initially x is d, this is x minimum. This guy is initially vx is u and finally it is 0. Then integration by substitution. Put u square minus vx square is equal to some t square minus vx dvx is equal to t dt. Limits also will change. This will become 0 to u and that will become minus t dt by t, and that becomes, that said, ln x minimum by d. Left side integration has become easy. That becomes minus u. So you get minus u by z exponential is x minimum by d. I skipped a step there. So, and then you're done. So x minimum would be d into e power minus u. And what is this z? Q u naught I by 2 pi m. So 2 pi m by mu naught q I. That's your answer. That all goes under exponential. And like we expected, if u is infinity, only then the term is becoming 0. Main idea is here. If you got till here, I think it got over. Physics after that, it's just as integration after this. Do have a look at this. And this is not the first time we did something like this. If you remember, we did a question like this, but in that case, the function was linear. This question, remember, b naught x thigh. Idea was the same thing I did. Say I took Vy, I took force, I took Ax, I did replaced Vy with this, I did the exact same thing. So it's not like completely new. The only thing I changed is the magnetic field. Everything else looks same. Do have a look at the steps. Clear, everyone? Next one. Clear na, Arjun? Neil? Udayan? Vidyut? Kush? Ishan? Rehan? Clear? Perfect. Next one. Force between parallel wires. So if you have two parallel wires, I1, I2, both are infinity. So technically you get infinite force. We can derive this. So this is force per unit length. That's how we define force per unit length. Is given by mu naught I1, I2 by 2 pi. Simply take the magnetic field due to one guy on the other one and do IL cross B. So if both the wires are having current in the same direction, then both the wires are having current in the opposite direction. So in this case, they attract. In this case, they repel. If the current goes in the opposite direction, they repel. You can easily check. So due to this current here, what is the magnetic field? It is into the plane, which is mu naught I1 by 2 pi d. And IL cross B, the force is left side. So the attract, you can just check it out. That's an easy derivation. We did more hopeless things before. So this is D. This is the formula there. Now the reason I like this formula well is because of units and dimensions. This is a very useful formula to find the dimensions of mu naught. In the exam, if they ask you find the dimensions of mu naught, which formula will you use? And this is something I keep telling you in units and dimensions, right? Whenever they ask you something, always try to find a formula related to mechanics. Like example, can someone tell me if you want to find the dimensions of resistance, which formula will I use? Right, Saina. Rho L by A. Rho L by A. Do you know resistivity ka formula? Someone said Ohm's law. V is equal to IR. Do you know voltage ka formula? Now you can figure out eventually, but but the thing is, keep it simple. Remember, power is equal to I square R. Power ka dimensions, I square is the current. Finish it off. If you say E into dr, then electric field ka formula chahiye. Capacitance ka which formula will you use? If they ask you dimensions of capacitance, people means they are going to ask you dimensions. Either means bit somewhere. Which one?
Q square by 2c.
Q square by 2c is a good idea, energy ka. So if I want to ask you for mu naught, this is a good one. Because I think mu naught is the, where else did you see mu naught? In magnetic field. Remember Biot-Savart's law? dB is equal to mu naught by 4 pi. Means you need to find magnetic field ka dimension. You will go mad. You will find magnetic field, you'll say F is equal to ILB. You can eventually figure out, but this thing I found directly give you in terms of force per unit length. Current is ampere. This is also length. So length goes off. So it is force by ampere square. So it is Newton by ampere square. So it looks Easy to figure out. Have a look at that. So that is one good use I found for this formula. For mu naught, I couldn't find a second formula which was purely mechanics ka terms mein. Let's see a question. Next one. That is the force per unit length. So we have an infinite wire here, I. So we have two problems here. You kept one wire like this, small I. This is a movable wire. Mass is M. Length is L. Parallel. The distance is D1. The second wire, let this be I1. This is parallel to this guy, I2, same mass, same length. Distance is D2. Gravity is there. So both the wires are at rest. This is an infinite fixed wire, okay? Both wires are movable here, both the wires are at rest. So I can ask you find D1, D2, but a better one would be, which of the following is in stable equilibrium? You can be at rest, but it can be stable or unstable. Which of the following is in stable equilibrium, and find the time period of its oscillation? Or both are in stable equilibrium, and find the time period of both of them. And find time period for small oscillations. If it's a main scale question, I'll just ask you which is in stable equilibrium. How do we do that? Try, you got 2 minutes. Okay, if you figure out the stability, then get the time period. Small oscillation, that is important.
That formula is valid only for infinite wires or for short wires. So
What?
that formula is valid only for infinite wires or for short wires also.
You can use it for short wires also. It's meaning at least one wire should be infinity. You can normally derive it also anywhere, right? What is stable here? A is stable if you had figured it out. Now, how do you figure out whether something is stable or unstable? This is how you check. Now, if you look at the forces acting on this, so this is mg, and the magnetic force between them is repulsion. So this is F magnetic, which is simply mu naught I1 by whatever is the distance between them, 2 pi x. Now, if this is pushed upward, if displaced up, then the magnetic force becomes less than mg, so this comes down. The mg will dominate, so it will come down. Isn't that what should happen in a stable equilibrium? Vice versa. If you had pushed it down, you always displace it and see whether you're coming back or not. If you displace it down, you're getting closer, then the repulsion will become greater than mg. Mg will never change, it goes up. This is a proper case of stable equilibrium. This is stable. This guy, the story is the same. Here, there's an attraction force, which is mu naught I by 2 pi x into length b aega. And this is your mg. Now, if I displace it up, you're getting closer. The magnetic force will become greater than mg. It goes up. It gets attracted. It keeps going up. It will never come back. So gone. There's no need to do the second part. This is unstable. Same thing will happen when you push down also. It'll just keep going down. Make sense? Then how do you find the time period? And you know how to find the time period in SHM. Displace it by small x, find the restoring forces, and then solve. So the upper one is in stable equilibrium. This is I, this is I1. Let this distance be D. 1 initially. Let's say you displaced it up by x. This is displaced up by x. We will take acceleration in the direction of x. It's a straightforward one. If you write the restoring forces acting on this, you have mg. This force will become F is equal to mu naught I1 by 2 pi d1 plus x into L. And this is your acceleration. So mu naught I1 by 2 pi L, take out d common, you'll get 1 plus x pi d1 minus mg is equal to ma, binomial approximation. This will be mu naught I1 L by 2 pi d 1 minus x by d1 minus mg. And we know previously when it is in equilibrium, these two terms were equal. That used to be d1 there. So that and this term will cancel off. So this guy and this guy will cancel off. So you'll be left out with minus mu naught I1 L by 2 pi d1 square into x. Bring that mass also downward is equal to a. This whole term is your omega square. Time period is equal to 2 pi by omega. Is that clear? You have to use binomial approximation, and that's why x should be small, or else you can't solve. Next one. Any doubts on this? So especially those questions, stable, unstable, equilibrium thing are important. Next one. Finite solenoid. So a solenoid is a tightly wound coil like a spring. Normally there's no space between them. The tightly wound coil. This is the radius r. This is length. N is the number of turns per unit length. Generally, this number will be huge, 2000, 3000 turns per meter. Since if you take 1 meter ka length coil, it will be pretty huge. So let's take a coil like this. So this is the point O. So from here, if you go to this corner, and if you go to this corner with the vertical line, let this angle be alpha and let this angle be beta. So the angle made by with the vertical line to the right corner, it's a finite length, is alpha, and the left corner is beta. This O is on the axial line. And now if you're sending current I through this coil, find the magnetic field at O. I hope the diagram is looking fine. The two corners, right, are making angles alpha and beta. Means if I make alpha is equal to beta is equal to 90, it will become infinite. This is a solenoid, basically a finite solenoid. Find B bar at point O. So O is a point on the axial line. So find the magnetic field in terms of alpha and beta. How would we start? Think for a moment, then I'll give you a hint and I'll give you 2 more minutes. 2 pages. This one. You need to always ask yourself, like, did we see something at least close to like this anywhere? At least if there is something close by, like anything like this. I feel the only thing which is close by to this thing is, remember, the field on the axial line. So can I treat like this? At a distance x from here, I can take a coil here and I can treat this point as a field on an axial line. And I'll find the magnetic field due to all these coils and then integrate them, isn't it? That is the idea there. Give it a try. So this question is something like this. You can treat them like, an infinite coils. And I'm asking you to find the field here. So this will be a field on the axial line. Try. I'll give 2-3 minutes. This one, remember that finite plate which we did? That one. So these are like important ones because standard results everyone knows. But if you take only finite solenoid, finite, current carrying plate, things get messed up. you know what, I n by 2 sine a plus b, yeah, something like that. So at a distance x, take a small thickness dx. So in that small dx, the number of turns in dx will be n into dx. So at this point here, the magnetic field, again, depending on how you choose your current direction, I'll just assume this way. So we get dB is equal to the number of turns n dx, and the formula is mu naught I r square by 2 into r square plus x square whole power 3 by 2. So if I take this angle to be theta, this angle to be theta, tan theta is equal to x by r. Substitute here, this will be dx will be r x square theta d theta mu naught I r square, denominator will become r cube into secant cube theta. This thing r cube cancels, mu naught I n by 2, r goes off, you get cos theta d theta. I think then you're done. Just take the limits there. So mu naught n I by 2 integral cos theta d theta. Limits will go from minus beta to alpha. I think it won't matter here. Even if you take that, you'll get still same thing. Mu naught n I by 2 sine alpha plus sine beta. Check. That's a good result. Minus of sine minus beta, right? Minus comes out. This is a result for a finite solenoid. If you take alpha is equal to beta is equal to 90, this becomes infinite solenoid. Now understand, in real life, so infinite solenoids don't exist. What it means is the length is much, much greater than r. If you take the length to be very large compared to the radius, you can treat that to be an infinite solenoid. And later on, we will prove in Ampere's law, even though we proved only on the axial line, we will observe the field everywhere is uniform inside. Yeah. We get B is equal to mu naught Ni. That would be another good standard result. Just like, how is capacitor in electrostatics? It's like an energy storing device, which stores in the form of electric field. Solenoid is our, device which stores magnetic energy. We call it an inductor later on. This would be our main device there. Is the derivation clear, everyone? Any doubts on this? Clear? Let me ask you one more thing. Suppose if you have a spring, conducting spring in natural length. What happens if you send current inside it? What happens if DC current is sent? DC current is constant current. AC current, which is alternating, like what we have. If sent. Options would be it will elongate, it will compress, it will oscillate, nothing happens. Or it depends on the direction of the current. ऐसा कुछ options होगा. Elongates, compresses, oscillates, nothing happens, depends on the direction of current. Are you sending it clockwise or anti-clockwise? What do you guys think? This is how they'll try my question. Okay. Don't ask me, na. You tell me, right? Confidently. Exam may come
Where is
and
the
shout
current
from.
going? Is it going inwards or it's going outwards?
So that option is also there, na. Depends on the direction of the current. It could be inwards or outwards. So that is also option there. It depends on that. Nee, Lakshika. Think. It's a good concept. Using this concept, I'll show you how to catch snakes. You can catch snakes using this. First of all, you should have snakes in the surrounding area. If you don't have snakes, you can't create snakes. See, what happens here, first of all, it doesn't matter how you send the current. Let's say if you send the current in one direction. So these are like, you can treat them like independent coils. So if you look at the field in the beginning, remember we wrote something like this. Each one will act like a magnet. That means if you look at this thing, if you magnet, this is north, south, this is north, south, this is like north, south, isn't it? And if you keep like this, the opposite poles, they attract. So the whole coil will compress. So if you're sending DC current, the answer would be the spring will compress. It doesn't matter which way you send the current. If you send the current in the opposite direction, then the magnets will be north, south, north, south. Sub reverse hoga na? It will still attract. But if you send AC current, now AC current you need to understand, current goes to 0 to maximum. So this will, it will compress, it will expand. It will compress and come back to natural length. It will start oscillating. Because in AC, if you send the AC current which you're sending in the house, the current is fluctuating and direction doesn't depend. But when the current is there, it will compress. When the current is gone, it will come to natural length. This will not elongate. Compression, natural length, compression, maybe due to some inertia, because the spring has a mass, it might oscillate a bit. And now, that is the answer, it will oscillate, getting it? Now what happens, right? If you look at the power supply in your house, it is 50 hertz. What is the meaning of that? Current literally changes every 50 times per second. That means this coil is expanding and compressing 50 times per second. So next time when you go near a transformer, observe that there's a sound buzz. There's a buzzing sound. That is because inside the transformer, the coils you have, the current when it is flowing, it is oscillating. It is oscillating 50 times per second. So literally, it is vibrating. So what people noticed, right? If you ever travel by train, you must have noticed as you enter the city outskirts, you'll find these big transformers and everything, power supply things. Because generally we keep power plants outside the city. So when you keep these transformers and everything outskirts, right? So these transformers are vibrating at 50 hertz. And these things, right? The vibrations are traveling through the ground. And snakes, right? They move based on vibrations. They don't see you. Movies mein dikhate hai na? The snake has looked at the villain, then it is chasing the villain. Oh, sab bullshit hai. Getting it? Snake has seen you once, so it will remember you forever. Nagin aa jayega. Next janm mein aake maar dega. This is all bullshit things. Snake doesn't have so much concept. Snakes, right? The mostly based on vibrations. And now what happens? Now you got a source here, and this is 24/7 vibrating, right? And these vibrations travel up to 100 to 200 meters radius. And any snake that passes by will get attracted to the vibrations. It will go. Maybe it will think it's an amusement park. It will go there. And once it goes there, it will observe a transformer is nothing but it produces heat also. There is a whole lot of energy being produced there. And snakes are cold-blooded animals. They love heat. So they'll go to the transformer, they'll turn around the coil and they sleep happily inside. Transformers are like the best. Transformer is like, an ice cream wala calling you and saying, free ice cream, come here. So due to the vibrations, the snakes will go there. Once they go, they realize it is hot and they say like, yeah, best. So what people noticed, right, when they installed transformers in the rural areas, when you go for maintenance after a month or so, it's full of snakes. Meaning, if there are snakes, they will get attracted to that. Now imagine a power company giving advertising. We will hire snake catchers. And you're sending a snake catcher and an electrical engineer for maintenance. So you can catch snakes like that. This is a big issue when you install transformers in rural areas. So what we do now, they build a small stand like this. They fill it up with, all the stone, sand, and everything to damp the vibrations. That's the reason, one of the reason transformers are kept on, something elevated, and you put a lot of stones. Railway platform mein hote na stones, track pe. They use similar stones there to damp the vibrations. So that is how you can catch a snake in case you want one. So that is one of the practical uses of magnetic field, catching snakes. Anyways, take a break. Come back by 7:07. We'll continue from here. Humans don't vibrate, true. Chalo, come back in 10 minutes. Yeah, comes on everyone. So the next thing is Ampere's law. Now, Ampere's law is again an experimentally, derived one. So what this says, the line integral of magnetic field over a closed loop is equal to mu naught times the current crossing the loop. So it's a line integral, kind of gives you vibes of, Gauss law, similar thing, mu naught I crossing. That means if you take any loop here, so this current is producing a magnetic field here. And if you try to integrate, dl bar would be along the loop. So this formula says if you integrate that b dot dl over this, you will end up with a mu naught into the I, the current crossing the loop. Now this is valid for steady currents. So when Ampere actually figured this out, people didn't know that, we have a time varying magnetic fields will create electric fields, or time varying electric fields create magnetic fields. This thing will go, this will not be valid. We will see that separately in EM waves. We have an Ampere's law, which is updated or, corrected one. But this works for steady currents. So if I take an example, we have a loop here. This is I1. This is I2. This is I3. This is I4. So integral b bar dot dl bar is equal to mu naught I crossing. Now this b bar is due to all currents. If you remember, even in Gauss law, right, that E dot ds, E bar is due to all charges inside and outside. Whereas this I crossing is only I1 minus I2. So the usefulness of this, so in this loop which you're taking, right, over which you're calculating is called an Ampere loop. Just like Gaussian surface is a surface on which you are calculating flux. So it's a loop on which integral b dot dl is calculated. E dot ds is called flux. B dot dl, as such, there's no name for this. So this Ampere law is quite useful to find magnetic field due to symmetrical current distributions. There should be symmetrical current distributions. Similarly, if you remember, Gauss law was useful to find electric field due to symmetrical charge distributions. Clear with this? Now we can take bits and pieces of it, and we can actually use Biot-Savart's law to prove this. Like I said, it is a reverse. This thing, Ampere's law, is more experimental. Biot-Savart's law is more powerful. Let's see how do we do this. Any doubts on this page? Clear so far with this? So it's straightforward. Integral b dot l is mu naught I crossing. This you should remember, quite useful, especially for advanced type of questions. Let's say we have a current wire I here. You take some random loop again. The same idea what we did. This is your dr bar, and this would be your this would be your rd theta. E theta cap is tangential direction, and this would be your dl. So this vector dl bar is given by dr bar e r cap. This is your radial direction. You can also say er cap, same thing. Plus rd theta, theta cap. This is your tangential direction. If you want to write this in 3-dimensional, then you will say zk cap. That will be your z coordinate. This is the out of the plane. So 3-dimensional way, that's what you get. dr, r, and z. You got all the 3 directions. And here we can see the magnetic field is mu naught I by 2 pi r. It's always tangential. Polar coordinates, works really well for this because the field is always tangential. Now, if you try to integrate b dot dl, it's not a. You will see you get a similar formula there, like what we did on the force mu naught I 2 pi r. So you should take only it's a dot product. So only the parallel component will matter. That would be rd theta. R will cancel. You end up with mu naught I by 2 pi into theta. So here you can see r cap is perpendicular to theta cap. Right, so that will be 0. You get a pretty nice result. That means if you take some random loop, it only depends on the angle subtended. This way. So you need not even have a closed loop. You could have taken anything. So if you take any random loop like this, and if you have like this, and if someone asks you what is the integral b dot dl, meaning over a closed loop here, this is A, this is B, this is current I. We will take this direction as positive. So b dot dl over this curve will be mu naught I by 2 pi. Basically, it is that formula, theta by 2 pi into mu naught I. If it is a closed loop, if this was a closed loop, remember the angle is rotating like this full. In this case, theta would be 2 pi. And then it will become integral b dot dl over a closed loop is that formula mu naught I. So we derived this with Biot-Savart's law. But suppose the wire is here and the loop is outside. Now what happens? When you go from here to here, the angle is positive. When you're coming back from here to here, the angle is negative. You're getting it? You're rotating theta and minus theta. So in this scenario, integral d theta would be 0. The rotations are opposite. So if the wire outside the closed loop will not contribute anything to integral b dot dl. Is this clear, everyone? Quite a useful one. So if I just give you some random loop and ask you, you can use this. Because amperes, this thing will only give you for closed loops. But if I give only part of the loop, this thing works. Have a look at this. This is a Good one. So sometimes you'll see in questions, right? They'll give you just a part of the loop, or they'll give you some 3-4 random wires and they'll ask you. So this will help.
So could you go to the previous page?
So indirectly, what we're doing here is we are choosing this as your x-axis and this is your y-axis, isn't it? Something like that. X you are replacing with the dr and y you're replacing with r d theta. You just need to have two perpendicular directions. All clear with this? Great. So let's see one question. Suppose if you have, we have a current wire I here. Let's say we have a loop B like this, C and D. Let's say this is L comma 0, this is L comma L, and this thing is that why is it bad? I want that to be 45. How will I do that? It's a 12 comma 12. This is 3L comma 12, something of this sort. I hope my coordinates are making sense, but okay. So find first one, integral b dot dl for AB, integral b dot dl for ABCD. I can ask you for any section actually. BC ka kitna hoga, CD ka kitna hoga. Each piece I can ask you. Let's do for AB and ABCD. The current wire is at the origin. Won't it be 12 for cos 45? ठीक है ना, that LL 12 12 the angles will take care. Okay. This is what I was saying now. Now, because you know the formula, it looks quite easy. But if you just give randomly, you literally have to solve. You will find the magnetic field and then you'll integrate and all. I don't know the answers. Right? Let's see. I'll show you in a minute. Get both of them. Second one, इतना अच्छा आंसर नहीं आएगा, I guess.
If you could make it 4L comma 12.
4L comma 12. क्यों, कुछ अच्छा होगा क्या?
हाँ सर, sin 30 बन जाएगा.
ठीक है ना, अभी गेट ना एंगल अभी क्या है? You know what, I by 8 for the first one. So for A to B, we just need to take this angle. This is 45. For A to D, we need this angle. Let's call it theta. Tan theta would be 2 by 3. बस इतना है और कुछ नहीं. So first one का answer would be integral b dot dl for AB theta by 2 pi. So that is pi by 4 by 2 pi into mu naught into I. So that is mu naught I by 8. The second one, I know the answer is not good. A, B, C, D, the angle subtended would be theta. And just leave it like this, na? Theta by 2 pi mu naught I, where theta is tan inverse 2 by 3. Easy? But there you go. It doesn't matter what shape it is, just join the ends, get the angle, you're done. Let's see something else.
It will be the angle from bottom or the angle between them.
We take clockwise direction. No, anti-clockwise is the positive. Right hand thumb rule.
No, the angle between C and D.
वो क्यों चाहिए? I asked you for ABCD, right?
I added both of them.
Why will you add up both of them? You just need ABCD का बीच का angle, isn't it? You're interested in this angle, corner to corner. बीच में I don't care what is happening, isn't it? Clear, na? It only matters end to end, isn't it? If you look at the loop here, I don't care what is the shape. I just interested in the two corners. Let's see something else. We have a loop here. We have a current wire. It is going like this to infinity. This also is going to infinity. Then it takes a turn. So the circuit is at, there's a battery at infinity there. And so the current is going in a loop like this. So this top part is finite. This angle is theta. This radius of the loop is r. So I will call them, this is wire 1. This is wire 2. This is wire 3. This is wire 4. See, current just cannot come out of nowhere, right? So it should come from somewhere. And they're carrying current I. So find integral B dot dl. Now, if you put that circle there, means it's a closed loop. Find integral B1 dot dl. This is also closed loop. Matlab, I want integral B1 dl only due to the first wire. So B1 is only due to first wire. So integral B2 dot dl, this is due to wire 2. This is due to all wires. Getting what I'm asking? So there is a loop. You need to find integral B dot dl due to the wire 1, wire 2, wire 1, wire 2. Now, sir, remember you asked something like this. Let's see how to do this thing. The first was easy, right? Mu naught I. Due to all wires, mu naught I. Done. There is nothing there, and the first was easy. How do you get B and C? Remember, wire 4 is at infinity, wire 3 is at infinity. Nere, B is wrong, na? Ishan, your B would be wrong. It only due to wire 1. See, understand one thing. Integral B dot dl, B is due to all current wires present, isn't it? That would be equal to mu naught into the current crossing the loop. That B bar is due to everyone. If you can't say only this guy is giving mu naught I.
हाँ
Even
वो तो है
wire
कॉन्ट
2,
कॉन्ट
yeah, even wire 2 is creating a magnetic field. Wire 4 create नहीं कर रहे because infinity, wire 3 is at infinity, so these two are gone, but wire 2 का field is finite. So if you just want due to that wire, So this is a finite wire formula, isn't it? So at this point, what is the field? This is theta. This is 90, isn't it? So B bar would be how much? Mu naught I by 4 pi r sine theta plus sine 90. That is a magnetic field. That would be this way, B bar, and DL is also parallel. So B bar is parallel to DL. So only due to wire 1, integral B1 dot DL, I can integrate the whole thing. This would be mu naught I by 4 pi r sine theta plus 1 into circumference 2 pi r. This is mu naught I by 2 into 1 plus sine theta. This is the thing only due to 1. I literally calculated the field due to the infinite wire, the finite wire, and I did B dot DL. It is not Ampere's law or nothing. Ampere's law only talks about due to all fields. Ampere's law doesn't know how to do for only single wire. Now, when we did that Ampere's law for the all of them, integral B dot DL, this guy was integral B1 dot DL, integral B2 dot DL. So summation of all 4 wires is that Ampere's law, integral B3 dot DL, integral B4 DL. This guy was mu naught I. Now, if you look at this wire 3, wire 4 are at infinite distance. This is infinity, this is infinity. So they don't contribute anything here. So this guy and this guy are 0 since wires are at infinity. So integral B dot di is mu naught I and integral B1 is mu naught I by 2, 1 plus sine theta. That means this remaining whatever is left must be due to the wire 2. You can calculate, you get the answer. Mu naught I by कितना आ रहा है ये? 1 minus sine theta by 2. You're getting it? Now you can ask, sir, can we integrate with this field? Now you tell me, can I find the field due to this and all these points? Symmetry nahi hai na? You can find the field on this circle, isn't it? Due to this wire 2, I can find the field on this circle. I can't find on this circle. The distances are not changing. So you can't do directly. But you can find due to wire 1, you can find on this because it is symmetrical. So there is no way to find wire 2 directly. You have to use the Ampere's law for the full. And then you say 3 and 4 are 0. And then 1 you can calculate and subtract. So there we used both Biot-Savart's law and Ampere law as a combination. Is this clear, everyone? Clear? Next thing. Now, like I said, what is the use of this Ampere's law? It is useful to find the magnetic field. So let me take an example. If you take an infinite wire carrying current I, this is what we do. Consider an Ampere loop symmetrically at a distance r. And by symmetry, we can see the field also will be in the same direction because all points are identical. Then we'll say use Ampere's law, integral B dot dl is equal to mu naught I. B will come out of the integral, so this is mod B, mod dl, both are parallel to cos 0. So integral dl will give you 2 pi r. Kind of like Gauss law, if you remember flux, we used to do that only, E into area. B is equal to mu naught I by 2 pi r. This is the field due to the infinite wire. Remember? We actually used integration to prove this, but this will give you the answer neatly. But like I said, the finite wire formula is more powerful. This is how you find this thing. Now using an idea like this, now you guys try this. We have an infinite hollow cylinder. This is just like hollow shell. It's an infinite hollow cylinder. radius r. The current I is flowing only on the surface, okay? Hollow, no? Inside it can't flow anything. So current I is flowing on the surface. Find the magnetic field as a function of x. X is the distance from the center. Second thing, if there's a magnetic field on this, there'll be a pressure on the surface. Find the magnetic pressure on the surface. Remember electrostatic field pressure, we'll have magnetic field pressure. That means this container is either trying to compress or expand. Anyone remember electrostatic field pressure ka formula? What is the formula? Denominator में 6 था नहीं रे drunkard 6 sigma square by 2 epsilon field pressure भूल गया क्या? Sigma is the surface charge density. Clear na Aryan? Let's get this everyone. If I give you an infinite hollow cylinder, find the field inside and outside and find the pressure on the surface. Whenever a current is I is going like this, the wire, right, something is happening. It is trying to compress. So it generates a pressure. Yeah, inside this field is outside, field is zero. You have to use Ampere's law. Outside, yes, it behaves like a wire. Pressure is the one I'm more interested in. Try a minute, I'll show you the field and then I'll give you 2 minutes for the pressure. Try to get for the pressure. When you send a current I through a hollow cylinder, it has a pressure. The cylinder is trying to compress. Anyway, if you ask me, sir, how do you know why are they getting compressed? Logically, so na. If you take this one infinite wire, all these are also wires only, isn't it? So, and when the current is going in the same direction, what will happen? They'll attract, isn't it? So every wire here is attracting this wire. So the whole thing is trying to compress. So internally, they're interacting between each other. The same way happened in electrostatics. In electrostatics, when you had positive charge, each charge is getting repelled by all the remaining charges that generated pressure on the surface. So an infinite hollow cylinder is an infinite parallel current wires. And when you have parallel wires, they do attract. And when they attract, the cylinder is trying to compress. So if you can send enough current, you can just collapse this. So for the first part, consider an Ampere law at a distance x. So we are taking x less than capital R inside. So integral b dot dl, by symmetry we can say b will be tangential. This will be b into 2 pi r. Current is 0, so b is 0. There's no field inside. Then consider an Ampere loop outside. That is for x greater than r. So here when you take integral b dot dl, now all the current is crossing the loop. So this is b into 2 pi r is mu naught I. So if you try to plot the graph, you will get the formula exactly like a hollow cylinder. There's no field, then suddenly there's a discontinuity and decreases. You should definitely remember these results. These things you can't derive them with Biot-Savart's law. Just like hollow sphere and solid sphere in electrostatics, hollow cylinder and solid cylinder in magnetism. How do we handle this? So listen, this is a little different. This I told you multiple times. Whenever you find the force between two things, what will you do? You take the field due to the remaining on this one wire and then find the force. Now, but what did we get here? The mu naught I by 2 pi r is the total field due to all the wires. So you can't take that. So this is what we do. We will take a thin slice here. The thin slice here, whose length will be r d theta. So you can treat this itself as a current wire. Let the length be L. The width is r d theta. Now, if you take a point just inside and just outside, this is the top view. This is our the red piece. So I will consider a point just inside one and just outside two. In case you're thinking, this was the same logic we used in the electrostatics also. Where was that? This one. Remember? We said we have a hollow shell. We took a small piece. We should take point inside, point outside. Yeah, then we said we proved then E1 is equal to E2. And then we said the total sum should be equal to half of the total field. You'll always get that. So now due to the thin slice, let's say the field is B, right? And the other one would be B dash. So B dash is due to all remaining wires. This is due to the rest of the cylinder. So B dash will be in the same direction for both of them. So this is like a wire, right? So direction will be reverse. So this is like a wire coming out here. So the field is going in circle. So here B will be this way. So inside, so this B is only due to the thin wire. Both will subtract. So B minus B dash, and that is 0. So we proved that small wire ka field is equal to the field due to the entire remaining thing. Generally, this is a thing you can remember. If you just remove that small wire, the field will be half of the total. And this outside will be B plus B dash, and that we proved should be mu naught I by 2 pi r. And you got both equal. So we found B dash is mu naught I by 4 pi r. Now, why do we need to do all this? Because when I calculate the force, I cannot take the field due to myself on my own wire, isn't it? So this is that strip. This is your current I. How much is the current here? This current I will be the total current I by 2 pi d theta. That is the current flowing here. And my magnetic field is B dash. This is your field B dash. So I L cross B, if you do, the force is inward. So if you see the top view on that small piece here, the current is coming out. I think I took B dash reverse. I took B dash reverse. Okay. Then Put your hand on this thing and rotate. So this would be the force dF. This is the side view. So if you see the entire cylinder, right, there are a lot of forces acting inward. All the cylinders trying to compress. And then what is dF? dF is nothing but ILB. So I is that guy. I by 2 pi d theta. Length is L. B is mu naught I by 4 pi r. There I got the force. And what is pressure? Pressure will be force by area. dF by, and what is the area? L into r d theta. So if you just shift everything there, L into r d theta, I end up with mu naught I square by 8 pi square r square. I'll write down the result in the next page. That LRD theta is the area of that strip. Do have a look at this. So the main thing is you can't take the full field. You should take the field due to the remaining things on this one thin loop. That will be half of the total. And then you're done. Force aa jayega. Force by area is the pressure. I'll give you an easy way to remember this formula. So let me just draw the final result here. So if when you have a cylinder like this, so when you are carrying a current like this, doesn't matter which way the current flows. Remember, the cylinder is trying to get compressed. The forces are inward. I didn't draw that properly. So there is a compression inside. So the magnetic pressure. So this is the third pressure you're dealing with. First thing was fluid pressure, electrostatic pressure, magnetic pressure. Modern physics we'll see field again, radiation pressure. And luckily, all these pressures they behave same way. Projected area, everything that works. So magnetic field pressure is what we got is mu naught I square by 8 pi square r square. Now, if I rearrange this a bit, multiply mu naught and mu naught. So this will be 1 by 2 mu naught. This will be mu naught I by 2 pi r ka whole square. This will be the magnetic field on the surface. This will be 1 by mu naught. This is the magnetic field on the outer surface. This is a total magnetic field on the surface. That's an easy way to remember. Just find the field outside and then you write half 1 by 2 mu naught b square. That's your formula there. So the pressure can be written as b square by 2 mu naught, where b is the pressure on the surface. That's the formula you know. It is just like a wire. And you can see the resemblance here. Electrostatic field pressure. When you wrote sigma square by 2 epsilon, this also, if you can multiply epsilon, and this will write sigma by 2 epsilon ka square. This is also nothing but half epsilon e square. E is the field on the surface. So if you take a shell here, plus q and radius r, the field on the surface is q square by 4 q by 4 pi epsilon r square. Q by 4 pi r square is nothing but sigma by epsilon. And if you remember, half epsilon e square is also energy density. Do you guys remember? So energy density is actually pressure. So I think the best way to remember is what is pressure, energy density. Done. That would be easy way to remember. And you can see the resemblance. Epsilon ka place mein 1 by mu naught, B ka place mein E, half is half. I think that would be a good way to remember. Have a look at this. clear with this? If you send current through the wires, they do compress.
That was the previous page.
Sir, I tried half loop लेके नीचे एक R miss हुआ. How did you
Half
get the
loop.
second R? Yeah, like we did in the sphere wala problem also. No, we took half loop and then we took the force of half loop on the other half, and then
I
we
divided
projected
by
area.
area ना रहे. I divided by area. यहाँ पे क्या projected area? What? Where is the projected area here?
If you take half the cylinder like this and the other half like this, so
So you're trying to
you can
find the force
project into
between,
flat. हाँ,
and
yes.
then what is the field
Force
there?
between two halves. So
God, what are you doing? Question पूछा था, find the force on the thin strip. Half क्यों ले रहे हो?
pressure निकालना ना, so we can find the pressure like that also.
Think you're goofing up. Sense नहीं बन रहा. You're doing something else completely. It is as different as idli and vada. Both look same size. Completely different. What you're telling is looking that weird to me. Socho what you're saying. The field, there is no field only inside. What is the point of taking half लेके क्या करोगे exactly? Your field is zero there.
हाँ, yes. So the field
The
of
pressure
one
is zero.
half on the
Story
other
over.
half. नहीं. So we can take one half of the loop which carries I by 2 current, and then we can find the force of that I by 2 current on the other I
Arre
by 2, no?
God, that half which you're talking looks like this.
Yes. Exactly.
You don't know how to find the field for this.
I know now. I think I know.
You know
On
every
the
point
other,
where you know at every
so
point.
no,
You
on
know
the other half,
you know on this thing. You know at this point.
it will be outward
So you
direction,
mean
no?
to
Like
say,
we can find a pair for each point.
meaning you can find the magnitude and all these things.
It should be radially outward only, no?
I'll
We
punch
did
you
the
now.
same thing for
ये
electrostatics also.
bullshit किया last time ने. Last time सिर्फ axial में निकालने के लिए इतना integrate करना पड़ा just to find on an axial line. And you're telling now you're going to find on this part.
Mm,
So you are a pro then. Find out and figure it out and let me know. I
so
तो can't
how did
find.
we do for electric current then?
I don't know. So on Earth, right, we are still undeveloped. We are not so highly advanced in maths yet. So in your civilization, if you can do so, please enlighten us. लेके solve करके लेके आओ. Let's see next one. You're talking about something else. I don't understanding what you're talking, but it is not making sense. तो try करके देखो ना रे. Solve करके मुझे भेजो. Answer आ गया तो अच्छा है.
I sent you something, sir. मतलब उसके along the lines में होना चाहिए.
Answer नहीं आया ना.
नीचे एक arc की कमी है, बस I got the constant exactly right. I don't know how.
चलो we'll see. That must have been operation failed, but patient survived wala types. Now we have a uniform cylinder carrying current I. It is uniformly carrying everywhere. This is like a solid sphere now. Find the field inside and outside. Find B bar as function of X. I can also define something called J, current density. Current per unit area. This I told you in electricity. This is the current per unit cross-sectional area. Let's find B of X. B part we'll give us a homework next class. We'll discuss. Find the pressure inside as function of X. So if you have a solid cylinder, you'll have pressure inside also. Do you remember solid sphere का pressure निकाला था हमने? In a gravitation में we did that. You can apply that half epsilon E square, whatever is the only for surfaces. It's a solid inside. Anyone remembers the formula for a solid sphere inside pressure formula?
सर उसमें क्या a square minus x square something कुछ आता था ना?
Rho square by 6 epsilon R square minus X square. याद है ये सब कुछ आएगा.
सर मैं 6 x के लिए कह रहा था.
I know, I understood when you said 6, I remembered that you were talking about this only. Yeah, that also I think we did an electro maybe kiya. Yeah, this was the formula. This was done even in gravitation. Pressure inside a solid sphere when you have uniformly charged. This was the result. I told you to remember all these things. Don't think like, I'm not saying you can't do in the exam. You won't be having time. You'll run out of time. If you can handle questions like this, you remember some standard results, it will save you time. And maybe that extra time you can use to do the tough questions. Let's find the field inside and outside. The pressure, you'll try it as a homework and then you'll tell me next class. We'll discuss that in the next class. Next class, we'll wrap up the chapter. I think first half we'll be done with the chapter. Then I was thinking we'll start with EMI. The bar magnets and all is all theoretical. We'll do in the end. Ek sath ratta maar lete hain. That is something like 8 to 10 formulas are there. So better we'll keep all that mugging up for 1 week. At least we'll be on a mindset, mug up karna hai week. Let's get this. We'll do EMI, electromagnetic induction. And after, I think modern physics, we will do bar magnets, optical instruments, units and dimensions and errors, vernier caliper, screw gauge, और क्या बचा है? Semiconductors तो है. Yeah, all that stuff we will do. All that is only for the mains portion. Same idea. Take a loop inside, outside, apply Ampere's loop and finish it off. Find pressure, that's a good one. Choosing an element and all. Take a loop here, distance x. So for r less than equal to r, integral b dot dl mu naught, this would be I by pi r square into pi x square. This would be b into 2 pi x. Mu naught I x square by r square. And for r greater than r, it just becomes like a wire outside. So I'll just write it down. 2 pi x is equal to mu naught I. So if you try to plot this graph, b versus x, this would be a linear function and then decreases. Clear? This I'll show in the next class, but tell me, what if I ask you this question, we have a cylinder here, and here the current is flowing J is equal to J naught R power 1. Matlab it is increasing linearly. Meaning at the center current is 0, as you go out, current is increasing. Can someone tell me how will the field be? This I told you in Gauss law to remember. If the current density is x power 1, or this way, if the current density is x power n, what is the field? Anyone remembers? In a solid sphere, if rho is equal to rho naught r power n, then the field inside is proportional to r power what? Drunkards. किसी को याद नहीं है कुछ भी. Telling you now, you forgot, right? That is fine. Now you forgot, you realize, now go back and revise. There, I put a star also for this. If the density is rho naught into r power n, the field inside is r power n plus 1. So here also it works. If this is j naught x power n, the magnetic field inside will be proportional to x power n plus 1. So there, we will prove that in the next class. Okay, with that we'll wrap up for the day. So do try this magnetic pressure inside and come. So next class, I think first half we finish off. We're almost done actually. We will just find the results for that infinite plate and all again using Ampere's law, which I've already done with integration. And then we'll start off with EMI. EMI is like rotational mechanics of electromagnetism. So like rotational mechanics is for mechanics, EMI is like for entire electromagnetism. So that is a good chapter. Interesting one. Okay, so with that, we'll wrap up for the day. So any doubts in today's class? Anything else you can stay back and ask, or else you're free to leave. So take